Hello everyone, welcome to the 2133 crash course. My name is Tom Hopkins and I will be going through the 2019 paper for 2133. This crash course was originally done in person, but unfortunately due to audio issues we've had to re-record, so sorry for the delay on that. So just to start, I will give an overview of what the exam looks like. So obviously it's 10 minutes reading time, 2 hours working time, and there's 100 marks up for grabs. You're given the two-port network parameters, as you can see here, and you're also given the small signal hybrid pi model, small signal models of the MOSFET and the BJT transistors. And you can also note that you're often given some important values for calculating transistor parameters. So you can see here we're given R0 is 100 kilo ohms, we're given beta, we're given the early voltage VA, and you're also given formulas for R out, you're also given formulas for the different capacitors, and you're given F of T. So with that out of the way, we will get started with the... Alright, so looking at question 1 here, we're given two amplifier circuits, common emitter and common collector configurations, and we are obviously told that the parameters are provided in the data sheet, and what we are needing to do is we need to find the input resistance, which is from here and here, which has been labeled for us, and we then need to find the mid-band gains for both amplifiers, and then have a look at their upper 3 dB frequency FH. You're given the option here to not calculate it and justify your response with a short explanation. We'll be going through the both sort of ways of answering that. So for starters, we're just going to start with the first amplifier here and answer A, B, and C for that one. So here is our common emitter amplifier. I've just redrawn the circuit here. And then obviously the first thing to do is draw the small signal equivalent circuit when we're looking at mid-band gain. So we've got the base, the collector, and the emitter of the transistors all here. And then, as you can clearly see here, this is where the base would be, this is where the collector would be, and then the emitter is this common ground point here. So we've essentially just taken this transistor and we've copy and pasted in the small signal diagram. I'll just give a refresher on what that looks like. So you can see here, this is where R pi was connected to, the emitter E here was connected to ground, and this was the collector up here, C. Because we're looking at small signal and mid-band circuits, the C pi and C mu capacitors, because they are quite small, will appear open. So that's why they have not been included there. So starting off, we need to find the input resistance here. So looking in from this terminal here, over here where Rin is, it's pretty clear that our input resistance, because everything to the left of this is not going to be seen, so none of this over here will be seen. So we're basically going to be just looking at R pi as our input resistance here. Now, what is R pi? We need to then calculate our transistor parameters. So I've got them over here. So these are the formulas for the different parameters. We need to find GM, we need to find R pi, and we need to find R0. The formula for GM is the collector current at DC over the thermal voltage VT, and then R pi is beta over GM, and R0 is VA over IC. So hopefully it was clear from the data sheet that we are given VA as 100 volts, beta as 100, and the thermal voltage is 26 millivolts. The thermal voltage doesn't really change, but I believe, yes, we have been given that here, so that is all good. And all we need to then do is find IC at DC. So when we do DC analysis, we get that to be 0.1 milliamps. And just to explain how we got that, so if we're looking at the circuit here, the IC collector current is here, which is the current into the collector. And thankfully for us, we are given a DC current source of 0.1 milliamps there. So it's pretty clear that we don't need to actually do any maths to calculate that that is going to be 0.1 milliamps. So we can just read that straight off. Now that we have our parameters, we can just simply calculate them, and these are the values that we get. which means our input resistance is 26 kilo ohms, and that is part A for the first amplifier. Moving on to part B, we need to find the gain. Obviously here, the gain is V out over Vs, and then just over here, looking at some working. So we can see here that V out is negative GM R0 V pi, and we get that by looking at this circuit here. If we look, this is clearly one loop, which means if you want to find the voltage V out, that's the same as the voltage drop across the R0 resistor, and given that the current is going this way, because this current source specifies the direction of current, it must flow like this in the loop, and that means that current will flow into the negative terminal of the resistor, which is why we then need to add a negative sign there, and then it's just Ohm's law. We know that the current is GM V pi, and then we times it by the resistance R0. So that is how we make this substitution here, that V out equals GM R0 V pi over Vs, and then we need to then find V pi in terms of Vs, and then we can simply substitute that away, and we do that pretty easily by, if we just look at the left side of the circuit, again, this is what it looks like in context over here, that's pretty clearly just a voltage divider. This voltage here is V pi, so we can just say that V pi is R pi over R pi plus 10k, and then we can replace V pi here with that. We can sub in our values because we know what R pi, GM, and R0 are, and then that is going to give us our corresponding gain value down there. Hopefully that's not too difficult. All right, now we'll move on to question C, which is where we are going to use the time constant method to find the FH frequency of this amplifier. So what I've done here is I've added back in C mu and C pi because we're finding the upper frequency bandwidth here. We need to add in these capacitors that we were previously ignoring because we're now considering frequencies at a much higher range. So they need to come back in. And earlier, the CL capacitor, the load capacitor, we excluded this from the circuit previously because it has a value of 1 picofarad. And again, this is in the same range as these two capacitors. It's very small, so it did not need to be included in our midband analysis or whatever. It was going to appear as an open circuit. So when we did DC and all of that, we were not including the effects of this capacitor here, but now that we're doing high frequency analysis, it needs to come back in. Again, referring back to the small signal equivalent circuit, the C pi is collected across the base to the emitter. Obviously the emitter is ground, and C mu is connected across the base to the collector. So that is, I've just drawn those in and connected them like that. This is what our circuit now looks like. And what we are going to do is we are going to find the Thevenin equivalent resistance looking into the terminals of each of these capacitors and then multiplying that by their capacitance values to get our time constants. So starting off, we're going to look at C pi. And you can clearly see here, when we're looking in from C pi, when we're doing a Thevenin equivalent circuit, we need to turn off all independent sources. So Vs is going to disappear. And then if we follow the connections here, we can see that these two resistances here are in parallel. And so that gives us a pretty simple circuit down here. It's just going to be 10k and 26k in parallel when we're finding the Thevenin resistance. Nothing too complicated about that. Then we're looking at C mu, which is a little bit more difficult because this is our Thevenin equivalent circuit here, and we've got some dependent sources, which is always a pain to deal with. So again, looking through the terminal of C mu, we can see that on the left we have V pi, and then over here on the right we have these resistances over here. I have just put R pi and the 10k resistance in parallel because on the left side here, just to simplify things for us a little bit, and that's how we generated this circuit here. Now, when we are doing Thevenin equivalent for these transistor circuits, a very handy trick is to, when we get to like a dependent source here, is to try and rewrite this whole part of the circuit here as some equivalent resistance. So sorry about that. Basically, what we have is the equivalent resistance down here, and I'm just going to redraw this circuit over here. So what we're doing is we're taking this circuit and I'm moving it over here, and we are saying what is the equivalent resistance looking in at this terminal here, which means we can take that whole circuit from this point and just replace it with a resistor in series, and we can add that up to find our Thevenin resistance over here. And while we're here, I'm actually going to just highlight a common trick that happens with BJT amplifiers. So obviously, this is our BJT with our base, collector, and emitter. And then the small signal equivalent circuit looks like this. That's our GM V pi. And over here is R0, and that's R pi and plus minus V pi. Now, a very handy trick for doing circuit analysis is to note that often this input current here, this is the base current, right? Because obviously the current going into the base, that's what it would look like here. And this base current equals I pi, as in the current through the R pi resistor. And what we know over here is GM V pi. We can actually rewrite this as GM times I pi times R pi. Again, that's just Ohm's law. This is the voltage across the R pi resistor, so we've just replaced it with the current and the resistance. And we know that GM is going to equal beta on R pi. R pi is going to equal beta on GM. That's just from the formulas that we saw earlier. These are going to cancel, and we know that I pi, as we said, is IB, the base current, which means that this dependent current source, it is GM V pi, but we can also rewrite it as beta IB. These are both the same things, and that comes in handy quite often. So, looking at this original circuit then, if we want to find the equivalent resistance here, it would be helpful to find what this current is, the current through the R pi / 10K resistor, because we know that this voltage here is still V pi. Even though we've put these resistors in parallel, they still have the same V pi voltage drop across them. And then we know that V pi is equal to the current through this combined resistor times the combined resistance. And that is a very helpful thing when we're trying to take this whole circuit here and then convert it into some equivalent resistance. Again, so what we do is we do KCL up here. We can see we have this current, GMV pi, we have our IN current, and then we have the current across R0, and this voltage here is Vn. And again, we are trying to find Vn in terms of IN, so we can replace this entire circuit with an equivalent resistance. This is very similar to what you do in two-port networks, method 3 of Thevenin. We're just finding the resistance from this input point, exactly like we did earlier with the input resistance of the whole circuit, and we're going to replace it with that resistor. So looking at KCL, it's clear that the current through here is Vn on R0, and then we have the current, and that's going to equal the two currents going out of the node. We've called it R pi. I've called it R pi here, but you can sort of think of this as just IN. This is current we obviously defined as IN, and then this current here is GM V pi. Again, we have just rewritten V pi as this current here, IN, times the resistance in parallel here, 10K. And again, just to make this really clear, if we look at the exact input point of this circuit, I've called this voltage Vn, and this is IN. We're just trying to find the voltage and current at this point from the perspective of this circuit so we can replace it with an equivalent resistor. We'll be doing many more of these in this exam, so hopefully this will become more clear, because it is kind of a weird thing if you haven't seen it before. But that basically gives us this circuit, and then we can say that the equivalent resistance of this circuit is this, just by dividing IN across and multiplying R0, which means, looking at our resistance from C pi, what we see is this resistance here, 7.2K, which is just 10K in parallel with 26K. because R pi is 26K, plus the equivalent resistance that we found over here. And then we can just sub in our values, and that gives us our resistance over here. That's for C mu. And then the equivalent resistance for CL is pretty simple. We get this equivalent circuit over here. Sorry, this should be a current source over here. But again, looking at the original circuit, we look through CL, we see the current source, and then we see R0. Obviously, we open all other capacitors when we're doing the time constant method, so we look at them one at a time, which means that's an open circuit. And because this circuit is entirely dead, V pi is equal to 0. Because of that, this source actually dies, which means when we're looking at this circuit, we don't actually need to consider this at all, which means RCL is just pretty clearly R out. So nothing too crazy about that. Then we just go down and we calculate our time constant values. So we use the resistances that we found, as well as the capacitor values. And looking over here, when we go back to the data sheet, we are given our value of C mu. Obviously, we know that CL is 1 picofarad because it was given to us here. And then we can calculate C pi by using this formula here. We're given FT, we know what GM is, and we know what C mu is. And that's how
okay, so we're going to move on to the common collector, common emitter amplifier, which looks like this. So to start off, let's just quickly cover how we get the transistor parameters. So our values from the data sheet have not changed over here. The only thing that we now need to recalculate is IC1 and IC2. I might just switch over to the original exam question over here, and we'll just quickly go over how we get these values. So looking at this circuit, when we do our DC analysis, this capacitor will be open because we're in DC. This voltage source will be turned off. Now, we want to minimize the amount of time and work we spend doing a DC analysis because we want to mainly focus on getting our AC analysis done as fast as possible. So, looking at this, it's clear that no current flows down here, and there's a DC current source here of 0.1 milliamps, and the collector current, IC2, is the current that flows into this collector. So it's pretty clear that that's 0.1 milliamps. For the exact same logic that we got IC is 0.1 milliamps up here, that capacitor's open, that source was dead. There was nothing too crazy about that. Now, looking over here, we need to find IC1 as well. This is a bit more difficult because we don't have a DC source up here just telling us what the current will be when we do our DC analysis. But one thing you might know is that IC is going to equal beta IB, and beta in this case is equal to 100, which means that IB is 1/100th of IC, which is quite small. And you can see that this is IB1, and that current there is IB2. So these base currents are going to be quite tiny. So if we make the assumption that these are approximately 0, then we can say that IC1 has to be this whole current through here, which means that it is equivalent to the DC current at this current source. So we can make the approximation and say IC1 is 0.1 milliamps. This is a very good approximation to make because it saves us the working out of going through and doing the full proper DC analysis. We can essentially just read it off, and it will not change our value significantly enough to be that important. I think IC1 actually will probably be around 0.98 milliamps or something like that, because these will be 1/100th of that. It'll be like some decimal approximation around there. Again, this is such a tiny amount that making this assumption will not change our value significantly enough to be worth doing the actual full analysis. And that is a really important skill to develop in these in the 2133 final, is making valid assumptions that simplify your working out. So my advice would normally be, if something seems quite difficult and you have a large resistor or small currents, you can just assume that resistor is open. You'll often make the assumption that R out is too big, so it's an open circuit. That's a very common one, but these are very good. And you will still get full marks if you make these approximations as long as they are reasonable. Aaron, in his working out, makes this exact same approximation that IC1 is 0.1 milliamps. So there's nothing too crazy there. And the benefit that gives us is that it means IC1 and IC2 are the same. So not only are these parameters for both transistors in this circuit, the exact same values. They're the same values that we calculated for the first transistor in question for the first amplifier, which just makes our lives much. All right, now we would want to draw up our small signal equivalent circuit for this thing, this circuit. So I've drawn up the base, collector, emitter. I've labeled all the nodes on each of the things. So hopefully, looking at the original circuit, it's not too hard to see how we got there. Again, I've left out the capacitor because it's going to be open, and I haven't included any of the internal capacitors for the transistor. All voltage sources, so these arrows here mark DC voltage sources, they are shorted to ground, and all the current sources have been opened. So that gives us our small signal equivalent circuit. And then part A, again, we need to find the input resistance from this point over here. So we can essentially do what we did earlier for the capacitors in the first one. I might draw it in here to make it a bit more clear. We can add in some dependent source here, Vin, if we can call it, and then find the current In. This is just method 3 of Thevenin. We're attaching a test source, or you can just think about it how we saw earlier. We're essentially finding the equivalent resistance of that point. If we find the voltage here divided by the current here, just considering everything to the right of this node, again, we can replace everything to the right here with a resistor, which means we could redraw this circuit like this. This is essentially what we're after for this question, the 10K, and then we find the input resistance, which means we'd be replacing this entire circuit over here with input resistance, very similar to what we did in Thevenin, nothing new there. So what we can start by doing here is, if we look at Vn, this is just KVL. If we go down this node, this voltage here, which we've attached as a voltage source, we need to find the input current. That voltage must equal the voltage drop across Vpi1 plus the voltage drop across Vpi2. And again, we want to find this voltage in terms of the input current. Now that's going to be equal to Rpi1 times In, because obviously In has to be the current flowing through that resistor there. And you'll notice that In, which is the input current from this voltage source, must equal Ib1. And that is where this approximation that we talked about earlier, this equation will come in handy. Instead of thinking about this dependent source as depending on GM Vpi1, it can help to think about it as depending on beta Ib1 or beta Ipi1, depending on however you want to think about it. And so what that means is we can replace Vpi1 again with Rpi1 times the current through at In, and then we know that this Vpi2 is going to be the base current of this second transistor, which again, this is Ib2 here, that's Ib1 here, if we want to look at it in the original circuit, times obviously the resistance there. And then what we know is that the base current, Ib2, must equal the input current going in here plus this current here. It might actually be better if I might relabel this as Ipi2, right? Because what this current will really represent is we can redraw this circuit as these two resistors here, R0 and Rpi2 in parallel. And then if we look at the nodes, I'll just draw it over here. This is our Rpi1 with our In current coming in. That is going to connect to this GM1, sorry, not GM1, we'll write it in this sort of substitution, beta IB1, or I might write it as In. And then this will be this resistor here, R pi parallel R out. So essentially, I've taken these two resistors here, which are in parallel. R0 is connected to this node and ground. This resistor is connected to this node and ground. So they're in parallel. That gives us the one resistor here, as we can see over here. And that voltage is still going to be Vpi2. So it would be better to think about this as Vn equals Vpi1 plus Vpi2. again, because V in as a voltage source is connected up here. And then we have the current through here, which is I in times R pi 1 plus, and then we need to find the current through this node, which has to be the sum of these two currents coming in. And these two currents are I in plus beta times I in. And I just want to make sure that it's clear where the beta times I in comes from. It's this substitution we made here. We know that this dependent source is V pi 1. We know that that's the same as the current I pi 1 through that resistor, and I pi 1 is the base current or the input current in this case. You can see that they're all equivalent currents. The input current is the only current through this resistor, the same with I pi 1, the same with the base current to the transistor. They're all the same, and this is where this kind of substitution trick really comes in handy, because now we can say that this current through the resistor is the sum of these currents times their resistances are in parallel. And that is essentially where this equation here comes from. And this is still equal to V in, which means that we can say that R in is equal to this, because V in divided by I in equals that. Again, all of these terms are now in terms of I in, so we can literally factorize that out and divide both sides, and that must be equal to I in. So you can see here, 1 plus GM R pi. I've just replaced beta with GM1 R pi 1. That's just from the formula. Hopefully you know that R pi 1 equals beta on GM. So then we can substitute out beta there, or you can leave it as beta. And then that's our values, and that gives us our equivalent input resistance. We'll be doing a lot more of these circuits with these kinds of approximations, so hopefully it'll become a bit more clear, but that is how you get your input resistance. All right, so our next task here is to find the gain, which is our V out on VS. Again, looking at this circuit over here, I'll just tidy this up a bit. Nothing has changed from the previous question. The output is still the exact same. We have one loop here, one current through that loop. It's going into the negative terminal. So it's pretty clear that V out is equal to GM2, V pi 2, R out 2. That's the same as what we did before. Now, a good way to think about solving these circuits is to find chains. We want to sort of build chains of different voltages. So I'll just remove all this because we don't need it. We want to find V out in terms of V in. And what that means is, because V out is pretty clearly, it's kind of disconnected from the circuit here, the link between these two, is V pi 2. So we can sort of think about building a chain. If we find V out in terms of V pi 2, we could then find V pi 2 in terms of maybe something like V pi 1, which we could then find in terms of VS. Or we could potentially skip this step entirely. But this is the sort of way of thinking that really helps in solving these more complicated circuits where we need to find the gain. It's we're baby stepping through, so we find one voltage in terms of VS, and then another voltage in terms of that voltage, and we sort of then rebuild the chain to get the output voltage in terms of the input voltage here. So that is, we found here V out in terms of V pi, and now we need to find V pi in terms of VS. Now, how we actually do? Yep, so we're going to put these two resistors here in parallel, R pi 1 and 10K, and then what we are going to do is we're going to try and find the equivalent resistance from this point here. And then if we find that, we can then voltage divide over it. Because if we replace this entire circuit here with a resistor to ground called REQ, then we know that the voltage at this node is V pi 2, because that's the voltage drop across this resistor, and that's to ground. And if we figure that out, then we can voltage divide, and that will give us V pi 2 in terms of VS, which is exactly what we would need to finally find the gain. So that this is essentially the circuit that we're trying to make, right? We have our voltage source, we put these two resistors in parallel, and then we look in from that terminal there and we replace it with a resistor to ground, and then we can find V pi 2. So to find the equivalent resistance from this point, you do not need to draw in this left part of the circuit here. I've just drawn it in to try and make this point really clear because we're going to be using this a lot throughout this exam. So I want to make sure that that's quite clear. And then we essentially just take this point. Again, that point there is the same as this point there. This is our V in, this is our I in. And you know, you can think about it as just connecting a voltage source to ground, whatever, however you want to see that. And I've just put these two resistors here in parallel and then said the voltage drop across them is V pi 2. All right, so I'll try and work through the logic of this equivalent resistance circuit more slowly. So over here, IB1, that's the base current, is the same as I in. Again, if we refer back to this circuit, let me tidy all this up. We're looking at the equivalent resistance here from this point. This is obviously our base current, as we said earlier, and this would be equivalent to our input current here. So it should be pretty clear that I in equals IB1. And then essentially, to find the equivalent resistance, I'm going to say that V in is the voltage drop across, it's V pi 2, it's the voltage drop across this resistor here, which is the voltage drop across, you know, whatever we get here. We then can use Ohm's law. So we know that a voltage equals a resistance times the current in this resistor. Now, looking at this node, we're going to use KCL. I might just draw the node over here. So we have this is I in, and again, that's where we're looking at the equivalent resistance from. That's connected to this dependent source, which is going to be beta I in, and that's connected to ground. Now, hopefully it's clear why that's beta I in. We've just used, we've replaced GM V pi 1 with, and we know that V pi 1 is equal to the current through that resistor times R pi 1, and then we do the same simplification that we did before. And that allows us to do KCL, so that means this current here is beta times I in, and that means that the current through this resistor here must equal these currents added up. So that's going to be I in plus beta I in, or IB or I pi, whatever you want to label that current, which means that V in over I in, which is the same as the equivalent resistance, is going to equal 1 plus beta times R01 parallel R pi 2, which means we can take this entire circuit and we can replace it with this resistor in parallel, REQ, everything to the right of that. And that allows us to do, if we look over here, a voltage divider, where we can say that, and I'm just going to rewrite this as 1 plus GM R pi 1, because that's what beta is equal to. And that is going to be what our equivalent resistance is. So hopefully, so with this knowledge of the voltage divider, you can see that this big chunk here is our equivalent resistance. This chunk here is also our equivalent resistance. And this is R pi 1 plus 10K in series, which was this voltage divider circuit we drew here. V pi 2 equals Vs times REQ over REQ plus 10K plus R pi 1. We've now found everything we need. So we sub in some values here to find what V pi 2 in terms of Vs is going to equal to. I will just comment on, you can see that I have made an approximation here. I have assumed that 26K in parallel with 100K is approximately equal to 26K, which is essentially like saying this resistor, R01, is actually open because it's too big. And these, you can check on your calculator if you want, These kinds of approximations are great because they barely change your answer and they just save you doing lots of complicated maths. And I've also approximated what those two numbers multiplied together are, just to make the working look a bit nicer. In terms of your circuit analysis, you could have assumed from the start that R out is too big. That would also be completely valid. I just wanted to show what it would look like without assuming that. Sometimes that's good, but it can make like finding, for example, the resistance here a bit difficult sometimes if you disregard R out. And oftentimes it does help, but you can see, and you can often avoid doing these annoying Thevenin equivalent circuits, but you can see here that even if we assumed this R out was too big and we got rid of it, that still wouldn't really change much of our working. We would just drop these parallel components and everything would be the same except a very slightly different number. So sometimes it's very helpful, and we'll see later on an example of where those kind of approximations are great, but I just wanted to show what the working would look like if you didn't want to make any approximations, but in the calculations, I've done that. You get V pi 2 equals this, sorry, this should be times Vs. And then essentially just sub equation 2 into equation 1, and we can rearrange for our gain, and that is our final value there. We'll now move on to C, and we'll look at the capacitor time constant circuit. So I will try and move a little bit quicker through this because it's a lot of circuit analysis. I'll show it on screen. You can verify it in your own time if you'd like, but we essentially are going to just look through each of these capacitors. We're going to open the rest of them when we're looking at it, and we're going to find the time constant similar to how we did before. One quick thing to note is I made a useful simplification where I found RE. Now, this is the value of RE, and I'll show you the working out for that, but this is the same as what we were doing before, finding the equivalent resistance. This is the equivalent resistance looking into the emitter of this first transistor. So this is the working out here for RE. This point here, this line is equivalent to this thing here. I've just redrawn it. It's very simple, similar working out to what we've done before. Beta IB, that's our IN, and this gives you an equivalent resistance value of 0.36K, and that's just if you see RE showing up in the working out, that's how we derived it. So we'll start off first by looking at our C mu 2, which is going to be this capacitor over here. You can see we did do the exact same trick that we did in the previous question. We find the equivalent resistance looking in from this point, which is the working out for that is down here, I believe. And you can see here that I've just rewritten this circuit as R pi 2 in parallel with RO1 in parallel with RE. Again, looking in from RC pi 2, it's pretty clear that this is the resistor on this side, this is another resistor on this side. All these capacitors are open, and because we found RE, we're going to replace RE with some resistor here, which means these three resistors are in parallel. That's how we get that equivalent circuit. A lot of this is just circuit analysis and algebra bashing, so I won't step through it too much, but the kind of tricks we're using is the exact same thing that we've gone through. We take a point in the circuit, we find the equivalent resistance for it, and then we make use of this beta IB trick over here as well a lot throughout this. So that lets us finding the equivalent resistance here. This is the working out for it. Again, you can see a lot of these, there's a very common pattern. You often get a dependent source with the R out resistor, and you often get the 1 plus GM times some resistance. This was the working out for the emitter resistance, and then you get RC pi 2 when we sub on our values equal to this resistance down here. Next is our RC pi 2. This is much nicer. This is just three resistors in parallel. Now, looking at our C pi mu, this is the equivalent circuit. We have 10K, R pi 1, and this equivalent resistor here. This comes from the circuit here. So again, this is our C mu capacitor. I'll try and tie it to our original circuit. So you can see that C mu down one branch is the 10K, then down another branch is R pi 1, and then that R pi 1 resistor flows down to here, and then we have this, and this branch all in parallel. So that's what the circuit looks like. We then find the equivalent resistance here. This is the working out for the equivalent resistance, which is then how we generate this kind of circuit here. This is approximately what Req is equal to, and then it's a much nicer working down here. Again, this is a 26K as well, and that gives us that resistance. This circuit here, we are looking at C pi 1. This one is quite frustrating to do, but you'll notice this node up here, this is what I called V plus, and then let me just try and tidy this up down here. Oops. This node down here is what I called V minus. So we're using method 3 again, we turn off our independent sources, we attach a test voltage source here, and again, what we're after is we're trying to find V test over I test, which is going to give us our equivalent resistance. So what we're going to do is we are going to find the voltage at the V plus node, find the voltage at the V minus node, and this V plus minus V minus will equal V test, because by definition, V test is the voltage across those two nodes. So to find the voltage at V plus, which I've labeled here, hopefully we know that V plus is the voltage drop across this resistor, and this is just Ohm's law. We use the fact that the current through this resistor must equal all the other currents. So obviously I test goes in here, this branch, and then this branch is negative V pi 1 on R pi 1. That is our current through that 10K resistor, just using KCL, looking at the sum of currents there. And then V minus, we are going to use a similar method. We're going to use KVL again to try and find the current through these two resistors in parallel. Again, this is just Ohm's law, so I might try and make this a bit more clear. This is our R, this is our I, this is our R, and this is our I. And we're looking specifically at IR in this branch to get V plus, and then to get V minus, we're looking at IR, which is the current through these two resistors in parallel. It's quite ugly, but what you'll find is that the current through these two resistors is this working out on the side over here. That's just, again, using KCL, looking at all the currents coming out of this branch. Sub those in, and then we know that V pi 1 is V test. So again, I just rewrite this a bit more nicely and do some expanding, factor out negative V test and I test from everything, move this expression here over to the other side, divide both sides by each other, multiply through by R pi. It's quite an ugly bash. We assume R01 is very large, again, to simplify this and this into just R pi and R pi, and then we get a nice calculated value there. Again, don't stress too much about the exact circuit analysis of this question because everyone will be different. The main principles to take away is that it's being able to use this V test and I test, especially here, being able to take a circuit like this where we have an ugly dependent source and then just find the equivalent resistance at this point and sub it out. Repeating a lot of the same strategies, very similar tactic used here with the emitter resistance again, which we found. And then CL, this is just equal to R out because for the same reasons that it was in the first circuit. V pi is 0 because these circuits are completely, V pi 2 is 0 because these circuits are completely disconnected, which literally just leaves these resistors as that dies. And that is the equivalent resistance for all these capacitors. And then we go down here and we can then find the time constants for all of them. I'm not going to spend too much time on it because it's the exact same. But what you'll notice here now is that the time constant from the load actually dominates now instead of the time constant from one of the internal capacitors. And that is a sign that we have removed the Miller effect, which has improved the frequency response of our amplifier. And we can see that here is the FH bandwidth is 107 kilohertz, whereas before it was 27 kilohertz. So this is much higher, which means our amplifier can operate over a much wider range of frequencies. So we have proven that the frequency response of the second amplifier is much. So to summarize, this is also applicable if you wanted to give a short explanation instead of doing all this working out. I'm not sure exactly how the mark distribution works because explaining the theory is probably much quicker than stepping through all this time constant capacitor analysis, as you can probably imagine. But essentially, the common collector arrangement reduces Miller's effect, which provides a wider bandwidth when compared to the common emitter configuration. As we know, common emitter amplifiers from the lectures have a Miller effect, and the common collector has no Miller effect. And by cascading these together, we can still keep the high gain of a common emitter amplifier while removing the Miller's effect. And we can clearly see that in action. We have 23 kilohertz bandwidth here with a massive time constant coming from the CMU capacitor, which is experiencing the Miller's effect. Whereas here, just by adding in that extra amplifier, our frequency response is much higher, which means that we have a much wider bandwidth. And the load is dominating, which is what you would expect, rather than one of the internal capacitors dominating the poles of the amplifier circuit. And okay, now we're moving on to question 2, which asks us to compare the stability behaviors of a single pole, double pole, and 3-pole system with negative feedback. And we're allowed to use root, locus, or Bode plots to support our explanation. So, for a single pole system, it's unconditionally stable. It's always stable because the phase shift is at most 90 degrees. Hopefully you know that when the phase shift hits negative 180 degrees, we get instability with a system that has negative feedback. And this is because if we have our voltage in, let's say it's some 0.1 millivolts, 0.1 volts, and it's at like frequency of 1,000 hertz, and it's got 0 degrees of phase shift. If our output, again, we're looking at the phase shift here from input to output. If our output voltage has a phase shift of negative 180 degrees, so like minus 180, sorry, this should be a sine wave. As we know from high school math, this is the same as the negative of this sine wave, not phase shifted 180 degrees. So a negative 180 degrees phase shift is an inversion, which means V out, will equal some gain times V in, but it'll be negative if our phase shift is minus 180 degrees. Now, the reason that causes instability is because obviously we need negative feedback for stability, and when we're feeding back some voltage from the output. If that voltage that we're feeding back has a phase shift of minus 180 degrees, that negative voltage we're meant to be feeding back to reduce the input is going to be inverted, which is going to make it positive, which means we will now be getting positive feedback. So if our phase shift hits minus 180 degrees, any negative feedback we have in our system will become positive feedback. So essentially, a single pole system means a maximum of 1 capacitor. And hopefully you remember from 2134 that because a capacitor is 1 over J omega C, that means, and multiplying by J or negative J is at most a 90 degrees phase shift. That means that only one capacitor, only one pole, the worst phase shift we can get is negative 90 degrees. So this is how you would draw your Bode plot. The pole causes the gain to decrease. Poles are created by capacitors. The most phase shift we can get is negative 90 degrees. For a two-pole system, we can have two capacitors, and our phase shift graph will look like that down the bottom, down here. And what that means is we have a phase shift that tends asymptotically towards 180 degrees. Technically, as you take the limit of frequency, you will get positive feedback, as at omega equals infinity, the phase shift will equal negative 180. But this is okay because by then the gain would be zero, and we would never be, that's not really a realistic thing that we would see in a two-pole system. So two-pole systems essentially are always stable with negative feedback. However, you can have, if you have a high enough loop gain, you can get some resonance and some oscillations, but generally you would say a two-pole system is always stable with negative feedback. A three-pole system, on the other hand, because we have three poles, we can pretty clearly drop below negative 180 degrees. That's our magic point there. And the phase shift can easily become negative 180 degrees, which means the phase is opposite in midband. So we would have negative feedback becoming positive, and that would cause instability in our system. I'll also just quickly show this is how you would explain question 2 using root locus diagrams. You're varying the magnitude of beta times the gain. And essentially for single pole and two pole systems, you would always have the poles being in the left-hand side of the plane, but when you add 3, they can drift into the right-hand side of the plane, which causes instability. Personally, I would use Bode plots because I think they're simpler, but for anyone interested, that is how you... Next, we're asked to explain base width modulation for a BJT and its implications for the small signal model, and then outline what's responsible for a similar behavior in MOSFETs. So, and it asks us to use a diagram. So this is the diagram of a BJT. You've got your emitter, base, and collector, and then we've obviously got the channels here. And essentially what base width modulation is we're assuming a given value of VBE. So obviously that's the voltage across the base to the emitter. As you change the voltage across the emitter to the collector, the size of the depletion width at the collector base junction will change the size of the base width. So basically, as we change VCE, we see this depletion region here is going to change in size. It's actually going to grow, and the extra green over here is basically saying as you increase VCE, we're increasing the size of that. So by increasing VCE, we increase the reverse bias voltage across the CB junction. So this is sort of what happens. You increase VCE, which causes the reverse bias voltage to increase, which sees an increase in the depletion region size. The size of the depletion region is increased, which decreases the base width. Hopefully that should be clear. So as we increase the size of this from here to now here to the green, the size of the base, which is, let's say it's an NPN transistor, our P-type silicon. As this depletion region increases, that means more holes and more electrons come together. That means there's less of these holes in the base. So we can see if this WB1 was the initial width of the base, we can clearly see that after we've varied VCE, causing the reverse bias voltage to change, causing the depletion region to change, that decreases the effective size of the base of a transistor. So here, an increase in the depletion region decreases the width of the base of our transistor. And since the saturation current is inversely proportional to the width of the base, IS, and hence the collector current will increase. So again, here's the change there, and that's from this formula here, IC is proportional to the saturation current. And essentially what this is saying is as you increase the VCE voltage, you are going to increase the collector current, and we can model that in the small signal model as this. The output resistance in our model is actually dependent on the change in VCE over the change in the collector current. That is base width modulation. Essentially, changing VCE changes the width of the base. It's pretty self-explanatory, base width modulation. And that's essentially the output. For a MOSFET, there's a very similar thing, which is channel length modulation. As you change VDS, the effective channel length reduces, which leads to an increase in R outs. I won't go through the full long explanation, but that's a MOSFET. That's what the channel looks like. Very similar stuff there. That is sort of, if you gave just you don't have to go into this much detail, obviously. What you mainly want to capture is the diagram, and you want to explain what base width modulation is, which is in the lectures, and then what they're looking for is this essentially means that our R out resistor, what we have its value set to will actually depend on VCE, and it's not just fixed, which is what the model assumes. Next, we're going to look at C, which is explain briefly the terms used to describe the performance of analog to digital converters. So we're looking at differential nonlinearity error and missing code. So the graph in white is your ideal step length of a digital to analog converter. These are obviously fractions of the reference voltage. And as you increase this voltage down here on the x-axis, this would change what code is picked up by the analog to digital converter. So yeah, on the bottom, this is our analog voltage. This is our digital output. And what differential nonlinearity error is, it's the difference between the ideal step width, which is these sort of gaps here. This is, your ideal step width, and the measured step width, which is in red. So obviously, ideally, we'd like our digital to analog converter to behave as it does in the white steps, but due to manufacturing errors, heat, there's many causes for this, you can get the curve being non-ideal. And you can see that you would essentially look at this step width and this step width here, and you would subtract them, and that would be your differential nonlinear error. And it's measured as an amount of the least significant bit. So each of these voltage is should be in the white. There should be 1 LSB volts apart. And if your differential nonlinear error is less than your least significant bit voltage value, then you're generally okay. But when you have differential nonlinear error that's exceeding minus 1 LSB, that means this red step width is so large that you're essentially skipping one of these voltage values. You can get missing code, which is sort of shown here. You can see in white, you have 1, 2, 3, 4, 5, 6, 7, 8 outputs, but in red we have 1, 2, 3, 4, 5, 6, 7. And we have a missing code where we're actually never able to produce the code 100 at the required voltage because our step width of the red graph is too wide in some areas, and it's causing us to skip over some of our code. So differential nonlinearity error is the difference in ideal step width versus actual step width, and if it gets too large, you get missing code. All right, now we're going to look at question D. So we've got a monostable vibrator here. The circuit can be triggered by applying a narrow positive input pulse of height greater than the reference voltage, and for normal operation, the capacitor and resistor C1 R1 is much less than CR, and the saturation voltages of the op-amp are VL and negative VL. So obviously that means the maximum values of this op-amp we can get are VL and negative VL. That's what it's being powered by. So in a stable state, what are the values of Vout, VA, and VB? So in a stable state, we're in DC, which means these capacitors are open, and the op-amp draws in no current, which means that VB will be sitting solidly at the negative V reference voltage because there's no current here, so this resistor is essentially dead, and we get V reference at VB. This capacitor's open, that means that resistor's dead, so our VA will be sitting solidly at ground. And then if we're looking at this over here, in this case, V plus is equal to VA, which is 0 volts, obviously, and we said VB equals negative V ref, which is V minus. Because V plus is greater than V minus, our output voltage here will be at the positive saturation. So just as a reminder for op amps, if V minus is greater than V plus and we don't have negative feedback, we go to the negative saturation voltage. If V plus is greater than V minus, the op amp is at the positive saturation voltage, and that is our initial values there. So the next question we were asked to do is show the waveforms of Vout and VA after the op amp has been triggered. So we are going to do that, and here are the waveforms here. So our waveform in green here, this is the trigger pulse. This is just some arbitrary horizontal pulse, which is obviously a magnitude greater than the reference voltage. This pulse causes VB to jump up by that amount. Because the question said assume C1R1 is much less than CR, we're not really going to consider these sawtooth kind of spikes that would happen as VB changes, because technically you have your spike here and you'd expect it to take time to go across this capacitor, but we're assuming that it's small and insignificant. So for the VB waveform, we'll just assume for the sake of simplicity that it follows the triggering voltage. So VB is just going to spike when VT spikes. And what that will do is as VB spikes, you can see VA in red here. At this point, VB, so previously, up like all this time before, VA, which is V plus, is less than VB, is greater than, sorry, which is V minus. Once we spike VB to a point greater than V reference, it's going to jump and be higher than VA, which will cause V minus to be greater than V plus, which will cause the output voltage here at this point to drop down to the negative saturation voltage down there. What this does is we now have our output voltage going from here, positive VL, down to negative VL. So the total change in voltage of the output is, so we have a negative 2 VL drop. So that means looking at here, V out goes from VL down to negative VL. So the voltage across this capacitor is going to drop by negative 2 VL. It's going to follow that, which means VA here, similarly, is going to have a negative 2 VL voltage drop down to here, and then it is going to decay like a normal capacitor until it reaches the value of VB, which again has gone back to V reference after it has stopped being triggered. And then now at this point here, suddenly V plus becomes greater than V minus again, which causes our output voltage here to spike up to the positive saturation voltage, VL. This again means that the change in voltage, it's gone from negative VL to positive VL, which is a change, it's a positive 2 VL voltage change. And that means that this voltage here is going to increase by 2 VL from this point. So this maximum will be like 2 VL minus V reference or something close to that value, because the main thing to note, is that that change there, it has a magnitude of 2 VL, and then it's just going to start decaying again. And then T here, this is the total time that the circuit is in the unstable state. So it's a monostable vibrator, which means it has one stable state. Its stable state is V out being equal to positive VL, and you can trigger it to cause it to drop into the unstable state, which is where V out equals negative. So now looking at part 3, we want to show that the pulse generated at the output will have a width T given by this formula here. So let's look at that. So obviously the voltage across the capacitor, hopefully you remember this from quad 1, is given by this formula, V final minus V initial, and then that's negative T on tau, where tau is the time constant of the capacitor. We then know that the voltage across the resistor here, this is really VA, is going to be V final minus the voltage across the capacitor. So essentially, this voltage here will be the final voltage that it's going to sell to, which is V final, minus whatever voltage drop is coming across the capacitor, VCT. And then that means that we can rewrite VR as this formula over here. Again, just taking VCT over here and subtracting it from V final. So we're just subbing this into this equation here. And that gives us our equation for VR. Now, we then know that our initial voltage, the initial voltage is going to be VL, and our final voltage is going to be negative VL. Again, because of the output voltage here, it starts at VL, and then the final steady state is negative VL. And then we just sub those values in to VR, so then we get VR equals that. And then to find the switching point, which is here, we want to know when the voltage across the resistor VR, again, this is VA, equals negative Vref. And hopefully that should make sense. We're looking at VA here, which is the voltage in pink, and we want to know when that's decayed down to negative Vref, because negative Vref is when VA equals VB, and that will be the exact switching time. So we're going to assume that like this switching occurs at t equals 0, and then we find the time it takes for this capacitor to decay down to V reference. That's going to give us the width of the pulse. So we then just sub those values in, and we rearrange, and we get this equation, and then obviously the tau of the capacitor is the time constant here is RC, because this is our, over here from the circuit, this is our RC, first order, single pole, whatever you want to call it, circuit over here. And that will give you the correct expression. All right, now we're going to look at question E. So we have a ladder type digital to analog converter, and we have these switches which are connected between V reference and ground. So when they're 1, it's V reference, and when they're 0, it's ground. And we want to find the output voltage in terms of the binary word. So one trick to these circuits is when we look to the left and right, they follow a very consistent pattern of what the equivalent resistance here is. So at this point here, just to the left of this singular R resistor, the equivalent resistance is R, and then at this point here, it's 2R. Then at this point here, the equivalent resistance is R, and it's 2R here. And the same rule applies looking to the right. There should be a R resistor here as well. So if we're looking to the right, this is going to be 2R, and that's going to be R. This is a very handy trick. You can just memorize this and use this to basically take any part of this circuit to the left here, whatever you want, and just replace it with their respective resistances. But we will try and derive some of that rule today. So essentially, it wants us to find the output voltage. So what we're going to do is we're going to look at the voltage contribution from Vref individually by considering all the other S switches. So when they're 1, this connection is valid. When they're 0, the ground connection is valid, right? So we're considering the voltage at node A-1, which is where this switch here is equal to 1, so that's connected to Vref, and then all these other switches are 0. They're now connected to ground. And then we can find the voltage contribution from one of those bits being 1. We can use the equivalent resistance formula hopefully to prove that. So essentially, let me just fix this. This should be R, and that should be 2R. So we know that looking from the left of this R resistor here, the equivalent resistance is 2R. Sorry, that should be 2R. That should be R. And then this should be, 2R over here. So that's why we can replace the entire left side of this circuit with 2R. And if you're not convinced that that applies, if we go over here, we can sort of just look. Over here, this is clearly 2R. Then if we want to find the equivalent resistance from this point, over here, everything to the left, we just have 2R in parallel with 2R, which means the equivalent resistance at this point is R. Then if you're looking from this point, you have R in series with REQ, which we said was R. So R plus R is 2R, and then the exact same pattern repeats. So here it was R, then here it was R, and then if we wanted to look here, we said that the equivalent resistance was R. So over here, this is R. From this point here, then we have a 2R resistance to ground, another R, and then 2R. And then again, if we look from this point here, this should be, there's an R resistor here as well. From here, this is 2R, and then this becomes R. And the same pattern sort of repeats. It was covered in the lectures, I believe. You can have another look into it, but that is essentially how we're going to show that everything to the right of this resistor here is going to, this was actually just like that. So that was R. That's our 2R resistance. And this is the equivalent circuit that we get when we're just considering the contribution from this node. So from here, we are going to try and find the voltage V plus, or the voltage at node n-1, and that is pretty clearly just going to be a voltage divider. So this is our first resistor 2R, and we're dividing across 2R in parallel with 2R, and that simplifies to this here, which means the voltage here is a third of V reference, which means the output voltage that node A-1 contributes is this voltage here, which is V ref on 3, and then that is fed into the input of a non-inverting op-amp, which is why we multiply that voltage by the gain of a non-inverting op-amp, which is 1 on R2 plus R1. So then we consider the voltage at node A n-2. Again, we use the equivalent resistance trick to take all the voltage on the left side here from this point here and say that that is 2R because it's to the right of the R resistor. Oh, sorry, not from that node there. It should be from this node here. And then everything to the right of that is 2R. So that gives us this equivalent circuit. Then we find the voltage at this node, which again is another voltage divider. So we are dividing over this resistor, and then it's 2R in parallel with R in series with these two in parallel. And then that gives us, that simplifies down to, again, V reference on a third. And then to find out how much of this voltage here gets divided into this node here, again, we want to find the voltage at Vn-1. This is another voltage divider, and we're dividing this voltage here down to this voltage here. So this is the first resistor it drops over, and then it drops down to these two in parallel. So to find Vn-1, sorry, this should be Vn-1 in terms of Vn-2. that looks like that, which gives us that Vn minus 2 is a half of Vn minus 1, and that is 1/2 of V reference voltage. And if you check, this pattern keeps continuing. Every node is a further and further half fraction of V reference on 3. So Vn minus 4 is going to be this voltage. That's the contribution. So Vn minus 4 will apply this much voltage to the node Vn minus 1, which is going to be what gets fed into the input of the op-amp. And hopefully that should make sense, because if we look at the whole circuit, if this node here is, we'll take this node here as an example, V2, and let's say that there's no more nodes, so then this node would be V3 and that node would be V4. V2 would have to drop half its value over here and then half its value over here, and that would be 1/2 squared. V1 would drop half and then half and then half, and it would be 1/2 cubed. And it's because the entire circuit is symmetrical, and every time you voltage divide from one node to the other, it drops by 1/2, and this equivalent resistance pattern holds. So you wouldn't necessarily have to derive this in the exam, but if you wanted to, it's just a lot of voltage dividers. But the final expression comes out to this. So what this is saying is, if this bit here is 1, this will be 1, otherwise it'll be 0 and won't get multiplied at all. And these bits pick up they all are a multiple of V ref on 3, and then the further away the bit is from the input of the op-amp, the less of a voltage they actually contribute to the final value. It becomes more and more of a fraction of 2, which depends obviously on how many bits the DAC is. And then obviously whatever voltage this is multiplied by the gain of the non-inverting op-amp, and that will give you your V. Okay, now we're going to look at question 3. So we have a 3-stage amplifier, and now we're looking at MOSFETs. Thankfully, they have given us the GM value for all the MOSFETs, and they're saying that's the same. And it's also important to note that if we go back to the formula sheet here, we actually have what R out is equal to, which is 100K for all MOSFETs. So that we don't have to do any DC analysis here to calculate our MOSFET parameters. We already have GM and we have R out. So we're good there. So the first thing it wants us to do is identify the type of feedback topology employed in the amplifier. So obviously there's the 4 different types: series, series shunt, shunt series, and shunt. And a quick and easy way to find out what the feedback topology of an amplifier is identify the input and output node of the amplifier as a whole, and then the input and output node of the feedback network. So here, the input node to this amplifier is marked in red here. It's obviously Vs, because that's our input voltage. And it says that the output is I out. So it's a bit tricky here because there's 2 labeled potential outputs for this amplifier. And depending on which one you picked as your output, that would change the topology of the amplifier. But here we're considering the current as our output. So that's the output of the whole amplifier. Now looking at the feedback network, it's pretty clear that the feedback network is RF. So the start of the network would be here, and then the end of the network would be here. And if these were the same node, if the input node of the feedback and the input node of the amplifier are the same, it's shunt. Otherwise, if they're different, it's series. So the input, these are clearly different nodes. They're separated by the MOSFET. So it's series. And then at the output, they're also clearly different node. So it's series. So that means your feedback topology is series. If it wanted us to take V out as our output, it would be series shunt. Because if V out was our output, then the output of the whole amplifier would be here. These are clearly the same node, so it would be series shunt. But for this case, we're looking at a series feedback topology, which means we are sampling, we're comparing voltages at the input, and we are comparing current at the output. So the question of whether to include this resistor in the feedback network, it's pretty clear that we should, because we're taking an output current. Again, there's no current through here, because there's no current into the gate of a MOSFET ever. You can see here that's labeled as an open circuit, even in the MOSFET diagram. So I out here, if we change this resistor, this would very clearly change the I out current, which would change how much of that current is being fed back. So it's pretty clear that we need to include RS2 in our feedback network. If we were sampling a voltage at the output, we wouldn't necessarily need RS2 because changing its value wouldn't actually change necessarily the voltage at this node. So it is actually important to also know whether you're sampling voltage and current to determine the feedback network. But in this case, this resistor would affect how much current is fed back. And because it's series at the output in our topology, we need to include that resistor in our feedback network. So looking at question 3, for A, I've redrawn the circuit. Series, current is being sampled at output, voltage is being compared at the input. We went over that. Now our feedback network is obviously these 3 resistors, and in part B, we are told that you may assume that the open loop gain is large, and we're trying to find the value of RF that results in a closed loop transconductance I out over Vs of approximately 100 milliamps per volt. So that is basically telling us that we want a closed loop gain of 100 milliamps per volt. Find beta that will give us this, essentially. Sorry, not closed loop, it is closed loop, sorry. So given that A0 is large, it tells us the open loop gain is large. This is obviously the formula to convert open loop gain to closed loop gain. But because A0 is large, this is going to be approximately equal to this. Because if A0 is large enough, adding 1 to it won't make that much of a difference. So the formula can be approximately written just like this, and then the A0s will cancel, and that's how you get 1 over beta. Now that is important for us finding our beta value. So now we're going to look at our feedback network. Topology is series, so we use Z parameters or impedance parameters, and our beta value is equal to Z12, and that is V1 over I2 with I1 set equal to 0. So we found V1 in terms of V2 here, and then we found V2 in terms of I2, and then this simplification here down to this is the working for it over here, just on the side. This is just rewriting stuff in parallel, sub 2 into 1, do some maths, and then we can say that V1 over I1 is equal to this over here, but V1 over I1 is beta, and we know what our closed loop gain is, and we know that our closed loop gain is 1 over beta, as we showed earlier, so that gives us a value of 0.01K for our beta value, and then using that we can solve for RF and get that as our final output value. Sorry, this should not be K. And that gives us the RF value. Okay, now we want to draw the open loop amplifier, taking into account the loading effect. So first we need to calculate what the loading effect will be. Again, we said we use Z parameters for this circuit. So we find Z11 and Z12. This will be the loading effect on the input, and this will be the loading effect on the output. Again, it's just 2-port network stuff, nothing too crazy there. And then we draw the small signal equivalent circuit here. Now, one thing to note when connecting the load resistances into the circuit, you basically find the start and end of the feedback network, which we've already found here. And then you take that node and you insert your resistor and then connect it to ground. Here, you take this node, insert your resistor, and then connect it to ground. Now, I'll just make a note for anyone interested. If we were looking at the output over here, and we were looking at the output node here, V out, this was our output. This would make our topology again, as we said earlier, series shunt. This is if we considered V out as our output, not I out. The feedback network would consist of RF and RS1, these two resistors, instead of the 3 we had before. And obviously we use H parameters, so that would make that H11. And then to connect this resistor, we would actually connect it like this in parallel with RS2, 1 over H22. Because this resistor would no longer be included in the feedback network. So the ending point of the feedback network would actually be here on RF. So that's an important thing to note in terms of that distinction. But that is not what they're asking us to do. So we would basically just connect this. That's our Z11. And then here is our Z22. Our topology is series, as we said. And then we no longer have to include these 3 resistors in the feedback network because they've been accounted for. So that's what our equivalent circuit would look like. Again, this was the source of the MOSFET connected to the feedback network. That's now connected to Z11, and the same thing over here. And this is our small signal equivalent circuit. Again, we already said we know what our parameters are. So now we have to do part D, which is find the mid-band open loop gain of the amplifier. So this is very similar to what we did in question 1. The idea is you want to break the circuit up into stages, right? So this is especially true for MOSFETs. You can see clearly that the circuit is divided up into kind of sections, and how these sections aren't actually connected by any wires, but they're connected by the dependent sources. So here, VGS1 is obviously VG1 minus VS, and VG1 is up here. So it's through these voltages that these circuits connect together. So a really useful way to approach these circuits is to break it up into stages. So imagine we want to find I out in terms of VS. That's our final goal. But if we found I out in terms of VG3, right, which is this voltage here, VG3, this is VG2, and then this is VG1. If we find I out in terms of VG3, we could then find VG3 in terms of VG2, and then find VG2 in terms of VG1, and VG1 in terms of VS, and then we could write out the different gains like this, and then we'd have our final gain. It makes it a little bit more approachable, I find, than just trying to attack this circuit in one go. So first off, let's try and find I out in terms of VG3. So for starters, we know that I out equals VS3, which is the source voltage, over Z22. Hopefully that should make sense, because I out over here is coming in, and then it will be split along these 2 branches, but the current out of here must also equal I out. So again, and this voltage here is VS3. So VS3 is that, and then we also use the fact that we use KCL in this node here, and we know that the current going in, GM VGS3, must equal the currents going out, which is VS3. This current here is VS3 over Z22, and then this current out here is VS3 over RO3. Because remember, this node here is ground, technically. I out is coming from ground, which is a little bit weird to think about, but that is how the circuit is shaped up. So this is just using KCL at this node here. And then this gives us this formula, because VGS3 equals VG3 minus VS. Again, that's just the VG3 minus VS3. That's from the dependent source. We're just rearranging here, finding VS3, and then subbing 2 into 1, and then we get what we want, which is I out over VG3, which is equal to this. Then we find VG3 in terms of VG2, which is not too hard. We know that over here, we know that VS2 equals 0 volts, because this is VS2 and it's connected to ground. That means that dependent source there is GM, this VG2, because VS2 is 0. And then we can say that we can take these 2 resistors in parallel, and then this just becomes the one loop. And we know that the voltage drop VG3 across these resistors would equal the current through them in parallel times the resistance of them in parallel, which is how we get this equation here. Again, VG2, this was GM VG2 as our current. Again, the negative sign because it's coming in from the negative terminal. This is very similar to what we did in question 1, times the resistance, which is them two in parallel. That then gives us VG3 in terms of VG2, and we get the gain that way. Now we can find VG2 in terms of VGS1. And here, this is an example of where we make the assumption. So we want to find here VG2 in terms of VG1, and this R0 resistor here is making our life very, very difficult. So previously I've been including all the R out resistors, but the circuit analysis becomes quite complicated. We could do another equivalent circuit here, like we've been doing before. We could try and replace this with REQ, but I'm just going to show you an example of, if you didn't want to do that, we're just going to clearly state that we are assuming that R01 is open because it's large, and that's going to simplify our circuit analysis much easier because we're going to say that VG2, which is this voltage here, is just going to be, then we can ignore this resistor, and then we just get a current going through down there. You should get this equation over here, and then we can find VG2 in terms of this, and then we find VS1 in terms of this. This equation over here comes from the fact that it's just Ohm's law. This is the current, and then the resistance is Z11. So looking at this, that's your resistance, that's your current, and then we can expand this out, right? So we just multiply this out, VG1, VGS. We move this term to this side, factor out the VS1, and then we get this equation, VS1 equals that. And then we can substitute 4 into 3, which was this equation up here. And that, if we follow the working, is going to give us VG2 in terms of VG1. And then our final bit, clearly VG1 equals VS. So that's the gain in terms of that, because by definition, VG1 is the same voltage as VS. So then we found all the gains we need for our final gain. And I believe that was 34.1 and 29. And that was 1. So if we go down to here, it's just about taking all these gains and multiplying them together, and then you get your final mid-band gain. The next part, so that's the open loop mid-band gain. The next part then, calculate the closed loop gain of the amplifier. This is very simple. It's just the formula to convert from closed loop to open loop. We know what beta is, 0.01, and we know what the closed loop gain is. We just found it. So make sure to note that this is in milliamps per volt, milliamps per volt. So this final gain will be in milliamps per volt. You have to be very careful of the units when it's not a voltage to voltage gain, but that's just simply subbing it into the formula, and then you get your closed loop gain to be equal to that. Part F, calculate the output resistance R1 of the closed loop amplifier. So we want the output resistance of the closed loop amplifier. So what we need to do is we first need to find the open loop output resistance. And then we need to, depending on the feedback topology, we need to either multiply or divide by 1 plus beta on A0. So because this is series at the output, we multiply by 1 plus beta by A0. If it was shunt at the output, we would divide by that factor. And R out is obviously our open loop output resistance. So to find that, we need to, if we go back to the original circuit, R out is clearly being taken from here. So we ignore everything above this. This is where the terminal we're looking in from, and this is the equivalent resistance. So even though there is a ground connection up here, we are going to ignore it and pretend this is not connected to ground, because it is behind from where we're looking into the input resistance. And then we're just going to do exactly what we did a bunch of in the first question. We're going to look at Vin and In, and then we have a very similar circuit to where we have a dependent source in parallel with a non-dependent source. You could assume R out is open if you wanted, but this is what you get. You get Vin. This is just using some KCL and stuff. So this is using like Ohm's law. You can look through the working. We've done a lot of similar stuff, but you end up getting R out over here equal to this. Again, we see the 1 plus GM times the resistance. This pattern keeps coming up a lot. It's a very common circuit. You'll get very used to doing these. We did a lot of these in question 1. That gives you your equivalent resistance. And then I'll just make a quick note here that I've flipped the direction of this current source because VG3 is 0 because that part of the circuit is disconnected, which means VGS3 equals negative VS3. So I've just written this as VS3 and changed the direction of the current source. Other than that, pretty standard stuff. Find our open loop output resistance, take that value, multiply it by 1 plus beta A0, and that gives us our final gain, our final output resistance value for the closed loop amplifier. The final question is asking us to assume the output is Vout. What will be the type of feedback topology employed in the amplifier? So we've already sort of discussed this. If I redraw the nodes over here, so these are all good, but we need to change where the output of the amplifier is. It's now down here. And again, we have the input of the amplifier and the input to the feedback are different. So it's series at the input. And then now the output of the feedback network and output of the amplifier are the same node. So it's series shunt. We're sampling a voltage. So changing the value of this resistance won't actually change the voltage here that gets fed back into the network, because whether this is 1K, whether this is 10K, it will change the current. It won't actually change the voltage. So we don't need to include this resistor in the feedback network, which is why this is what our feedback network would look like. And as I said before, you would use H parameters, and that would sort of change where you connect your loading resistors. They would be connected like this, and this resistor would be taken out. So you would have to include RS2 in your open loop circuit. But it doesn't ask us to do any more with that, so that's it. And I believe that concludes the exam. So thank you everyone for watching, and good luck on your final exam.